And to also recognize, so confidence intervals. Confidence intervals are interval estimates that basically give you a 95% interval within which you're 95% confident that it contains the population mean. It's calculated basically by adding or subtracting from the mean the set score of interest. So if you're interested in 5%, it's 1.96 multiplied by the standard error of the mean, because this is what you use to standardize your differences.
Where'd you get 1.96?
From the set score table, because 0.96 corresponds with 2.5% tails on each side. So you have 1.96 corresponds with 2.5% probability on both sides. If you go to minus 1.96, you have your 0.025, which is 2.5% on both sides. You always need to look at this in a two-tailed test, always from both sides. That's actually the next slide here. So you want to quantify here this 95% area under the curve that basically contains 95% of everything under that curve, and you only leave the tails with 2.5% on both sides out. And this is basically, if in this region you find your population mean, you are rejecting your null hypothesis that sample mean and population mean are identical at an alpha level of 5%. And with calculation of the set score and the formal hypothesis testing, you calculate the exact p-value with which you're rejecting your null hypothesis or accepting it. So this is basically the confidence interval and how you're using the confidence interval. So again, this is the calculation of the set score. We're calculating the mean, m, of the sample minus the population mean, mu. We're dividing it by the standard error of the mean. So we're having the difference of our sample mean from the population mean, and we're standardizing this difference by the standard error of the mean, which is the hypothetical distribution of the means around that mean. So that's the variability of these means. So you're using this for hypothesis testing. You're getting with the corresponding p-value to that set score, you get an actual probability with which you assume the null hypothesis is correct. If that is smaller than 5%, you're rejecting this null hypothesis and accepting the research hypothesis. This p-value essentially is also a quantification of the type 1 error. So essentially with the alpha, and keep in mind the type 1 error, this is basically rejecting something that should not be rejected. So the rest p-value smaller than the 5%, that's the remaining type 1 error rate risk. So the alpha is basically determining your acceptable type 1 error that you're willing to accept in your analysis. So this determines your critical values on your distribution of your differences. So when it comes to effect size, the problem with this is really that the standard error of the mean is strongly affected by the sample size. If you have a larger sample, your division of the standard deviation from the population is actually by a larger number. So the square root of the n is still an increasing number with larger sample size, and it will lower your standard error of the mean. So larger sample size, you get a more accurate estimate of your mean, and thereby you get a division by a smaller denominator, and as a consequence, you get a larger set. If the set is larger, you're more likely to reject your null hypothesis. That means that sample size, unfortunately, leads to large sample sizes, like really large sample sizes, will very likely lead to rejection of your null hypothesis, which doesn't necessarily mean it's clinically relevant or relevant difference. It's just rejecting it because of the large sample size. Therefore, effect size is quite interesting in that regard, because it mitigates and lessens the effect of the large sample size. Because with effect size, you're basically paying attention to the fact that large sample sizes may result in significant effects. So it basically means to take this effect of the sample size out and puts the weight back on the difference rather than the sample size. So, and essentially it means to quantify how much two populations do not overlap. So now you have two ways how to do that. So one, so the quantification here is really that you have here differences in those differences between two groups. So you have here two identical populations, and there's a difference. So if the difference is larger, the effect size is going to be larger. Second possibility is you have two identical differences. So this is a difference, this is a difference, and what's different here is the variability. With a narrow variability found on the lower graphs. So that also will result in a larger effect size, because it is the amount in which these populations do not overlap. So to quantify this and put the weight back on the difference rather than the sample size, the effect size was quantified, and this can be quantified by calculating Cohen's d. So that's basically the mean, the sample mean, minus the population mean divided by the standard deviation of the population, and not by the standard error of the mean. So this is what you will be doing, and we will be doing this later. So you're basically quantifying d as a marker of the effect size, unaffected by the sample size. And then you will, in the next step, you will quantify this d in the light of these conventions, where you basically call a small effect size a convention by Cohen's d between 0.2 and 0.5. The medium-sized d would be 0.5 to 0.8, and the large effect size would be everything greater than 0.8. So that's a way how to take sample size out of the equation and put the weight back on the difference. Yes. So the more a population overlaps, the more likely the null hypothesis will be true, right? If the differences are further, less overlap between the population will result essentially in a greater probability of the null hypothesis being rejected. You can do this either by increasing the differences. So if these differences are larger, less overlap between two populations will occur. Or with a smaller variability, you will also get less overlap. So there's all this overlap. So if these go apart, this will decrease the overlap. Or if the variability gets less and the distributions get skinnier, then there's also going to be less overlap. That is the effect size convention, Cohen's d. That's the convention as per Cohen. So that is one approach. And so there are different approaches to quantify effect size. Cohen's d is just the most commonly used one and the simplest one. It's basically taking the effect out from the sample size by using the standard deviation. That for a set test, for example, is given, as per definition, it's given. Yeah. So in the same context, the meta-analysis is basically a way to aggregate the results of different studies. So we talked about study and replications. So you have different levels of evidence. So you have the lowest level of evidence is basically where you go back into historic data that has been accumulated or collected for different reasons, and you look for signals in this data. So you see whether, I don't know, diabetics and non-diabetics have different blood pressures. That would be a retrospective analysis. from over 10 years and collected in hospitals on a routine basis. You can then also do prospective studies where actually you design the systematic data collection of a certain population and you compare it against another population that you also systematically study and collect data from. You can also do prospective interventional studies where basically you have a certain intervention that you test on a certain population. That would be in the highest level of evidence would be a randomized controlled study where you basically you don't give an intervention to one group and you give an intervention like blood pressure medication to another population and you study them both moving forward and then you compare the difference at the end of a study period. You can then, if several studies of that kind have shown some form of an effect size, you can actually get to the last level of scientific evidence where basically you take all these estimates, these replicated studies, utilizing the same standardized approach, you put them together and you amalgamate them in what is called a meta-analysis. So basically you have here a graph that shows you effect size estimates of different studies. They all showed quite large effect sizes, and you basically use amalgamate and aggregate them into one overall effect size estimate. We basically utilize data from all these different studies. Yes.
And how do you read that, like,
Excuse me?
how do you read that from the left bottom?
This one? How do you get that? So they're talking about the mean estimate. So that would be the mean of these effect sizes. It's not that easy. So usually you use very sophisticated and advanced models to basically not only factor in the individual estimates, but also the variability that led to these estimates. So you basically you put weight on each individual estimate based on the variability. Because if there's more variability, you need to account for that in your overall estimate, because a study with a lot of variability should have less weight in your estimate as one that has little variability. Like this one has less, this has less. So you basically you factor in variability and you get to this overarching aggregated estimate. It's quite a sophisticated model that you would use. But yeah, it's basically it's an overarching aggregated mean effect size in its simplest definition. Yeah.
But not something that.
No, I will not make you go through that process. That would be not fair. But basically, when you think about this now, it gives you a solid estimate of what this effect size really is, right? You put all these studies together, you get one overarching effect size. So if you include now a number of different studies that did not show a significant effect size, and they had a so-called null result, a negative result, negative finding, this would basically have a weight in this too, in this estimate. And it would slowly push this estimate towards null. So basically, if you include null studies that don't have an effect size, this would slowly push this overarching effect arithmetically towards the null as well. And therefore, we have the so-called file draw analysis. That's basically a statistical simulation or calculation of how many studies you would have needed to include that had a negative result, a null estimate, a null effect on the population, to essentially take the significance out of your statistical overall effect size. So this is basically called a file draw analysis, under the assumption that a study that is negative and did not show a significant effect is more likely to end up in a file drawer and never gets published. Because meta-analyses are, as you can think, they're done on published literature. So you basically you find all the studies that have been published on a certain topic, show the certain result. You take this result and you quantify it in your model with just the effect estimate and the variability, and then you create this overarching effect size. So if studies were not published and they ended up in a file drawer, this hypothetically may have lessened the true effect. And you mean to estimate how many of these studies must have existed to basically render these effects as negative. So it's a simulation to kind of tries to convince the reader and kind of presents to the reader how solid that estimate actually is. Yeah. And then lastly, we're going to speak about statistical power, and we did already last time. And statistical power is actually the probability that you will be able to avoid a type 2 error. And to understand type 1 and type 2 error, I really highly recommend memorizing this table. So you basically have here two true statements. One true statement is here, you have no effect. Then you will fail to reject the null hypothesis and you will accept that there's no difference between, if I set test, for example, between your sample mean and your population mean. That's a correct decision. The type 1 error is that you essentially have to reject the null hypothesis because the probability of this null hypothesis to be true is smaller than 5%, then you will reject it. So you basically, if you reject erroneously, and it's basically there is no difference, then you're basically committing a type 1 error. Of note, type 1 error and this correct decision adds up in a probability to 100%. So there's only, it's true, there's no effect. You can either make an error or you don't make an error. And you accept the null hypothesis. Here on this column, you basically also have 100% probability. If you have an effect, you can either make the correct decision and reject the null hypothesis, or you don't make the correct decision and you're not rejecting it. This is again adding up to 100%. So the type 2 error, so type 1 error is the acceptable threshold is alpha. That's usually 5%. Type 2 error is the so-called beta, is usually set at 10% for very rigorous studies, or can always be in some you also find 20%, but usually it's 10%. So again, 10% and the leftover of 100% is 90% of power. So you strive to achieve 100% power, 90% power. And to calculate the statistical power, you essentially need a mean, a standard deviation, sample mean, sample size, standard error determined on the sample size. You need a critical set value, so you need the alpha. And then you can basically, using the sample size, there's quite a complex formula, allows you to actually estimate the sample size needed that you need to study to achieve power that is as an desirable magnitude of 90%. But so this is the
Why don't you want 100%?
Well, because that would be the absolute truth. It's impossible to estimate the absolute truth. There's no absolute truth.
It's too precise.
Accurate would be the term. So there's no accuracy, right? Nothing can be determined with accuracy.
So then you just want to get it to the highest it can.
It is a reasonable, let's put it that way. So these are all nonlinear functions, right? This is all nonlinear, essentially, because when you have the normal distribution curve, this is a function that basically will never, if you think of this, so you have an x-axis and y-axis, and the y-axis is the count, and then you have the model function. These functions, these tails that we're quantifying, and you see that essentially when you follow along with the z-score table, these will never approach. These are asymptotically never approaching the x-axis, because there is improbability. There's no certainty. Certainty doesn't exist, right? It's like you can. This is even the principle of quantum mechanics, that you will never be able to determine the location of an electron with absolute certainty, which you may have heard about that. And so there's no certainty. So 100% by definition is impossible. And this is just a reasonable estimate that basically you can use to kind of get an acceptable level which you're willing to accept. But a certain error you always need to accept.
You're always looking for 90%.
Well, it is a convention to go for 90%. Yeah.
That's beta.
That's the no, it's the power. Power is 1 minus the beta. Beta is the type 2 error. This error. That's the beta. That's beta. That's alpha. And these are the respective others. So that's the confidence interval, right? And that's your power. So hypothetically, what you can do to increase your power is by increasing an alpha. So this is increasing the type 1 error you're willing to accept, rather debatable practice. You can turn a two-tailed hypothesis into a one-tailed hypothesis, also quite debatable. Statistical reviewers are gonna roast you over open fire if you really try to do that. Not really, of course, but so they don't like that. Like literally, like I'm not sure I've ever reasonably read a statistical paper or any scientific paper that would work towards a one-tailed hypothesis. Then you can increase the n. Problem is with increasing the n, you will need to study substantially more people, which will result in substantially more costs, substantial prolongation of your study period. So it comes at a price, right? Exaggerating the mean difference between levels of the independent variables. So that would be, for example, you increase the dosage of your blood pressure medication, which is one possibility, but then also sometimes not practically possible, physiologically plausible or possible, sometimes not even ethically acceptable. So there are many reasons why you could not do that, right? So, but these are the four main factors that affect statistical power. And yeah, so here's the graphical depiction. So basically the power is that area that does not overlap between the population and is also basically exceeding this critical value. So that's your power. So you have two possibilities. You increase your alpha, you get a larger free area that constitutes your power. Secondly, you can also do a one-tailed versus a two-tailed test. Then you basically always on one side rather than on both sides. So this basically leads also to an increase in your power. Again, debatable practice. Then you can increase your sample size, which will in turn decrease your standard deviation and your standard error, which is the costly way to go. But basically it will decrease the variability in your sample. Actually, it should be standard error, not standard deviation. It will basically decrease your variability, thereby leads to less overlap, thereby increasing the power again. And lastly, you have increasing of the difference for the aforementioned reason, also complicated things to do, but another way how to increase the power. So now the interesting question is, why would you need to know the sample size? You need it when you estimate the sample size you need to study for your study, right? And you would do this usually. So when you design a study and you propose a study to a funding agency, for example, you would go and you would find every literature that ever studied the very same research question. You would find the mean differences they found. You will try to quantify the variability that they have reported in their data, and you will try to estimate all the different parts that are needed to estimate the power. And then you will simulate a couple of scenarios through. And you will, based on that, you will say, I need to study 50 patients, 100 patients, 1,000 patients to achieve this statistical power for my study. And that's when you strive for the 90%. So in the wider picture, it's like, why do we set an alpha? And why do we set a beta? We're setting this acceptable levels to essentially prevent patients from harm. Because if you assume there's a difference with a medication and you rely on that medication, you need to know that was a certain level of, I hate to say it, but confidence rather than certainty So you basically you try to protect future patients that will be prescribed to the drug, will receive the drug. Or with the type 2 area, basically you try to mitigate useless research that is basically underpowered and doesn't really give you the information and the certainty in your estimate that you actually would need. So these are the two main reasons why you set these maximal levels of an error that you're willing to accept. Good. Any questions on that? On any of this? Because if not, then I would like to commence the lab day. And so we're doing today a little exercise. So we have, start this new. So we are essentially looking today at 2 examples that are posted on your Canvas as practice lab 2. So again, I'm well aware I will not be able to teach you R coding over the course of a semester, accompanying stats. So that's why I'm making this R coding exercise as simple as possible, but I also want to make them as useful as possible. So every exercise we do in Excel will be accompanied with the same exercise in R, which you can do with it whatever you think is best. I just want you to submit proof that you did run that code. And maybe one day you're going to look at it again, and maybe it's going to be useful to you at one point. I think it will be if you do some scientific activity, if you choose to use R and not some of the commercial softwares. But basically, we're doing this code today. So we have 729 and 730 as examples coded in R. And I will walk you through this exercise in Excel, that you know how to do those calculations. And we have done already an example when we did hypothesis testing. We did cholesterol. If you remember, this was this example where we used, no, I closed it already. That's not good. So we did cholesterol and we compared the sample of smoking hypertensive males to the general population. So we had, if you remember this, we had here 2 set of tests to a general population that had 211 milligrams per deciliter. So I highly also flagged these slides. They were posted in module 9, sorry. And these basically graphically outline and walk you through these calculations, how you calculate actually these p-values. And we're going to do this today with an example that I've chosen from Nolan and Heinz's book. And this is to show you that this basically, it always follows the same outline. The calculations are done in the same fashion. And that's the beauty of statistics. The methodology doesn't change. It's the same methodology. And that's why I also do this exercise to walk you through Excel and R, because I want you to see that the outcomes are the same and the methods you're using are essentially performing this in the same way or fashion. But the key of statistics is not, it's to some extent knowing how to use a certain tool, but it's mainly how to employ whatever tool you choose. And that is really, that's where the real skill of statistics is. Nowadays, you can do in R, I can in 5 lines, I can code the most advanced analytic methods that would have taken people 50 years ago, probably like 5 days to calculate what I can do in 30 seconds. But the application hasn't changed. So since the 1970s, when they started working on advanced analytics, the method hasn't changed, the application hasn't changed. The methods have just used another form of being conducted. Yes? The Word document is in assignments practice lab. Should be on your module at the very end, module 12 rather at the end.
Third module.
Yeah.
Which one?
Module or on the assignments. It should be on both.
And do I need to open R or Studio?
Our studio, please. Our studio, please.
Studio?
Mhm.
Okay, then I
So it should
Studio
look,
where I had them before.
yes, but it will do that for you. Yep. So you need to download it. You need to open it in our studio. So you open our studio first, and then go on File and Open. And there you can select the file that you have downloaded.
How do I make these?
You need to first download the file and open it in our studio.
Wait, you open it in R Studio?
Yes.
Silas module 9, you said?
This was a module 12. Okay, so the example here is we have a sample of 50 people for whom you observed the mean verbal score on the SAT, university admission test in the US, of 542. So your sample mean is 542. And this is also part of the exercise, essentially. Read the questions, understand the questions, what it is providing in each particular sentence of the question. That's actually what's most important for the quizzes and for the exams. So you have a sample mean of 542. You have a population mean of 500 and the standard deviation of 100. So what do we need out of that? We need basically the three pieces of information it gives us is we have a mean, a sample mean.
Should we open up Excel also?
Yes. We have a sample.
In our Excel sheet?
No, you don't have to hand in the Excel. You can follow along or not follow along, up with me. I need you, I want you to have the recording that you can go to each steps of this calculation. Right?
If I just look at yours in order to do it,
If you don't want to follow along, it's like I'm not forcing you to do that. These Excel examples are for those of you that are more visually inclined, as I am, for example. For me, it's easier to calculate something through, and then I understand it. If I just sit here and I look at the professor telling me something about concepts, I will not be able to follow myself just by listening to me. These calculations would be essential for me as a student. That's why I'm doing them. Yeah. Okay, so we have a sample mean of 542. We have a population mean, mu, of 500. We have a sigma of 100. And the size of the sample was 50 people. So that's our n. So the n is 50. Simple, right? So as the first step, so we have quantified now, all what we need to understand from this population, except for one thing, and that's step one. You need to calculate based on your sample, you need to understand what would be the distribution of these hypothetical sample means, right? So that's easy. We're calculating the sigma, which is our population standard deviation, divided by the square root of the n. Simple. So that's our SEM. Yep. I copy it right next to it. This is the standard error of the mean, SEM. This is the calculation. So it's B3 sigma divided by the square root of B4, which is the sample size. So that's this formula that we have calculated in the context of the central limit theorem. That's the relationship between the standard deviation and the standard error of the mean. So when we know the standard deviation of the population, we will be able to estimate, based on that, this hypothetical variability of these hypothetically drawn means around our sample mean. We can now utilize this standard error of the mean to do hypothesis testing and to test whether our sample mean of 542 is significantly different from our mu, our population mean. So we will do that by essentially first we need to determine an alpha, right? So what is an alpha we're comfortable with? This will be alpha 5%, just as always. We're basically assuming this as being our alpha. So the critically set values would be minus 1.96 and plus 1.96. So now we want to calculate the confidence interval, right? And the confidence interval is essentially demarcated by our negative 1.96 set score and our positive 1.96 set score. And this can be done by calculating the mean, not the mu, minus, so okay, LL and UL for lower limit and upper limit. Lower limit is sample mean minus 1.96 multiplied by our standard error of the mean. That is the lower limit of the confidence interval. Yes, I copied the formula right next to it. So this is the formula. So this is the formula. The upper limit, the same fashion, is mean, sample mean, plus 1.96 multiplied by the standard error. This will give us 569. So just looking at these two values, this is our 95% confidence interval. Well, we're comparing this now to our mu, which is the mu of interest. That's the value of interest. What can we conclude out of that? You add this. Yes. So now you have the lower and upper limit of the 95% confidence interval. The mu is smaller than the lower limit. What is the conclusion? They're not the same. Exactly. They're significantly different. So you did already hypothesis testing right here. You solved the question whether you're going to reject or accept the null hypothesis. You will reject it because it's significantly different. In a two-sided test, because you defined 2.5% on both sides of your distribution. Yeah, I gotta refer you to the recording, unfortunately. We need to carry on. Okay, so we have now a calculation to be done for an actual set. So the set is calculated as the difference between the mean minus the mu divided by the standard error of the mean. And that is our set and a two-sided test, right? Yeah. So we're calculating this formula, the formula which we use for the set testing and hypothesis testing. So that I would highly recommend to review before the midterm next week. So we have here set equals mean minus mu divided by the standard error of the mean. Yes.
How did you get the UL?
Well, this is this formula. You just need to make it plus.
Okay.
Again, I highly recommend to review these formulas. So there will be calculations on it. So really practice these calculations. That would be really would be a pity to lose this point. Okay, so this is a two-sided hypothesis test, right? So in a two-sided hypothesis test, what is our null hypothesis? Our null hypothesis is here that the mean equals the mu, right? That is the null hypothesis. The research or alternative hypothesis is that the mean is not equal to the mu. But this comes from programming, means unequal. So it's an exclamation mark and equal sign. So this is the research hypothesis, right? So we have determined that with a certainty less than 5%, our null hypothesis may still be true, but the probability is certainly smaller than our alpha. So we're looking essentially at accepting the alternative hypothesis because we know it's outside. Now we just need to determine how much this probability actually is that this still could be true. And this is what we're doing now with the set of converting the set into P. And this P is a little bit tricky to do because you only want those tails, right? And when you think of this, how can you quantify this tail? This tail is quantified by looking at the negative entry for your minus 1.96. So you're looking at 2.97, right? Use the calculation. So our set is 2.97. So 2.97 here corresponds to minus 2.97 corresponds with 0.0015. So that's 0.15%. Excuse me? That is P on one side. That's one tail. It's just one side. And that's where the trick is. And I'm flagging this for the quizzes. Know how to distinguish those two. That's why we're doing this now. So we have only briefly brushed over one-tailed hypothesis testing, but I want to do this now. So we have 2 multiplied by 0.0015. So our actual P is now 0.003, which is 0.3%. This is 2 times the p-value that you have determined from your set score table.
Are you able to put it so like it's 2 times?
Yeah, it's 2 times 0.0015. And 0.0015 comes from a set score of minus 2.97. That's the left tail. Now you know it's a 2-tailed hypothesis, so you need to calculate it twice. So there are 2 tails to be considered. That's why I multiplied by 2. You have a corresponding example you have with the cholesterol example, module 9. You have the same thing. You get minus 1.74. That was 0.041. Multiplied by 2 gets you to 8.2%. We had not rejected this null hypothesis. Now we're doing this ourselves in Excel. Good. So now when you come to a 2-sided test, now you also want to do a 1-sided test, right? So with a 1-sided test, you have a directional hypothesis. So now hypothesis number 1, look at this formula. If the mean that you're looking at here would be larger than your sample mean, so the mu larger than the sample mean, by definition, the numerator needs to be negative, right? Because if you subtract something that is larger from something that's smaller, that becomes a negative value. So the numerator becomes negative. If you divide something negative by the standard error of the mean, this will still be negative. That means you essentially now looking at a left-sided hypothesis because everything to the left is negative, right? So this left-sided hypothesis has a research alternative where the mean is smaller than the mu. So when this is your research hypothesis, the absolute opposite needs to be your null hypothesis, correct? If something is unequal, then the null hypothesis is equal. If the direction is that the mu is smaller than the mean, the null hypothesis needs to be the exact opposite. So that means that the mean, the sample mean, needs to be larger or equal to the mu. Yeah. So now how do I calculate this? In exactly the same fashion. It's the same calculation. It's the mean minus the mu divided by the standard error of the mean. The only thing that changes is now that the classes or the angle you're looking at this. And this is again in these slides that I've shown you, because what we're doing now is essentially we're looking at the left-sided test. So we're interested in one set score, and we're interested in everything to the left of it. So this being said, if I have 2.97, which again will be the outcome of this calculation, when I have 2.97, positive 2.97, notably, because the calculation is our M is 542 minus 500 is 42 divided by 14.14, which is the standard error of the mean. So this 0.97 is essentially what we're interested in. So it's a positive set score. So we need to go on the other side of the table, and we're looking for 2.97, and we get here the p-value of 0.9985. So p of 0.9985, would I reject this hypothesis? Exactly, no. I'm accepting the null hypothesis, and I do not reject, here accept the null. And that's in the cholesterol example. This is this example. So it's the opposite to our example, but it's basically everything above. All right. Hmm? Yes, yes, yes. Yes, it is. Right there. So it will become clearer if we do now the opposite, because now we're doing the other way around. So now we do right-sided. Now we see, no, that's, so now we're hypothesizing that the mean, sample mean, 542, is larger than our mu. M larger mu. What's the corresponding null hypothesis? That the mean is smaller, equal our mu. The calculation again is exactly the same. Nothing changes. But what's the corresponding other hypothesis? Because now it's going upwards, now it's going to the right. It's still 0.9985, but it's now the leftover above that set score. So it's 1 minus equals 1 minus 0.9985. And that's our 0.0015. And now we reject the null. Okay. It's quite logical. It's not difficult. It's essentially just, and this is why I think it's a good idea to draw up this normal distribution curve, because these subtle differences in interpretation may be subject of some, during an exam, you just get mixed up, you may confuse one versus another. So that's why it makes sense to draw this normal distribution curve. But the concept is super easy in principle. Any questions? Yes.
Concept that you're referring to is that if you're above like
Yeah, that's one of those concepts. Yeah, no, but also two-sided, left-sided, right-sided. So it really, what you need to follow is the research hypothesis to the negative. It points downwards because you're hypothesizing. So you're hypothesizing that the difference between your sample mean and your population mean is actually pointing to the left. It's left-sided. It would be rather negative, right? If your mean is larger, it would be negative. Yeah.
If I make two normal curves next to each other, the sample mean would be to the left.
Well, the values don't change, right? It's just the angle you're looking at. So if you're interested in having in testing versus the lower part of it, that's actually what you would be interested in. Okay. You're welcome. And so now the last thing we have to do, and we have 8 more minutes, which is terribly little, is now the R code. And it doesn't really matter because I think, yes.
Sorry, just before you start, when I clicked the R code from Canvas, there's a bunch of wording at the bottom.
Did you download it?
Yeah.
Yeah, just start RStudio first and open it from your RStudio with open file. Yeah? You click on file and open file right here. Right here. There's open file and you just find it where you downloaded it. So going into RStudio. So basically we remember now that control and return, control and enter will basically run a line, right? So if we run line 2 in the code, this essentially cleans your entire environment. And we talked about this code that's basically removing everything that's contained in the environment. So we will then in the following on line 5 to 8, we will basically assign values to the variables mu, n, sigma, and x bar. X bar standing for the sample mean. So these 4 values essentially you're defining here in your calculations.
Wait, you just press enter for all of them?
Control enter. Control enter.
So is it command enter for me?
No, control.
Is there a backspace?
So control enter will basically run each line.
And also for STEM?
Yes, so the standard error of the mean basically is line number 9, which is a calculation in the same fashion as we have done it in Excel, but basically now just expressed here as exactly those variables we have defined at line 5 to 8. So you will then in the following in line 11 and 12, you basically quantify our set score, which is 2.97. You will then in line 15 and 16, you will then quantify our detailed p-values, which is here 0.002979. So it's 0.003.
Are you supposed to be putting these numbers in? Are you supposed to be putting these numbers in?
No, you just run the code.
Oh.
Did you find the code on Canvas?
Yeah, yeah.
Oh, okay. No, you just need to follow along the code. You just press Control and Enter, yes. From the first one to the, slowly down. The p-tailed smaller calculation is essentially a calculation of this p-value. So p-norm set is essentially a calculation of the actual p-value. So this is just a function where R basically provides this function. This function also exists in Excel, but I think for practical purposes, I think it's easy.
The value though, when I ran the whole proof, was 0.1.
Yes, because there are 2 exercises in one code.
So
So you went to the second exercise.
So the first one.
So you need to go back to the first exercise.
0.9985103.
Yeah. So here we have 2.97. We have a p-value of 0.015 for the one-sided. Then we have on line 34, we have our lower and upper limits with 514 and 569. We have here calculation of the effect size. That basically is here a medium-sized effect size of 0.42. And then we get to exercise number 2, which is exercise 7.3 in the book, which basically is the same example. So by this time we have a larger sample. We have 132 people. We have again the SAT scores, and in this sample it was 490 now. The population mean is still 500, standard deviation is still 100. Now we're basically going through that example of 7.3, and we're doing the same estimation for 7.3. So this again, we have a mu of 500, so we're cleaning the environment at line 45. We're assigning mu, sigma, x bar, and n on line 46 to 49. We're calculating standard error of the mean on line 50, and the actual set scores on line 53 and 4. We're calculating two-tailed p-values, which is here 25%. We calculate one-tailed and another one-tailed in both directions. And we're calculating our upper and lower. So good question. So these are actually comments. Everything that is in green that has a little hashtag in front is basically a comment, which is basically explaining what happens on the lines to follow. No, you can leave them in. Nothing happens if you run them. It's just, it's making a comment. It's kind of you helping your future self. So as an analyst, if you're analyzing something and then 2 years later you have to revisit your own code, you will not remember anything you did. So you're helping your future self essentially remembering. That's the purpose of comments.
Mine has like additional work. Yeah, like additional like bullets or whatever, like the arrows. That's okay.
I don't know what additional arrows you had, but if it's after hashtag, it's fine. Yeah, then there's no problem. So these are the lower and upper limits of the confidence intervals. Then we have effect sizes calculated, and there's also the conclusion to this effect size. So as for the deliverable for practice lab number 2, you click now in the console, you press Control and L, which clears the console entirely. You click in the script, you press Command and A, and then Control and Return. That will run the entire code. You now
run it like all twice.
Yeah, just clear the console first, run the entire code.
Wait, something weird happens.
And then copy the entire code.
Wait.
You have it on the recording.
Oh, wait.
You have now the spotlight. You type in text edit. And in the text edit, you're going to start the text edit. And here you basically have a blank document for the text edit, and you command V copies and pastes the entire copied console content in. It's the same that you did for practice lab 1. No, please don't do a Word document, do a text edit, please. Are you on a Windows computer?
Yes.
Please do a text document. Make a right click in a folder and click on New. There's text document. Or copy this in a text document and save this as a TXT file, please. Because otherwise it's not readable in Word. Please save this file then with a description of your course number, your name, your family name, and practice lab 2. All right, thank you very much. Have a nice evening.
Do you mind helping me save it as a text document just so that